Good evening to the students of class 12. Let us continue with the chapter number 3 and let us discuss the topic of drift velocity of the electrons in a conductor, related topics like current in the conductor and the mobility of a charge carrier in this video. I am Dhanu Sareya. Keep watching till the end so that these topics are understood by you very clearly and you can apply the formulas for the numericals very well. These topics and formulas are very important for the numerical point of view, both in the NEET, JEE as well as for the CBSE formats of question papers. Now we discuss about drift of an electron, that is drift velocity. Now let us consider a conductor with no electric field given to it, such that the electrons collide with each other and with the static immobile ions inside the conductor, such that it follows a path as shown by the yellow soft line. After every collision, the speed remains the same, but the velocity, that is the direction, changes. And consider that this particular electron has started from A, has the successive collisions and has reached the position B after colliding with the various ions on its way. Fine. So now let us write down that the electrons collide with ions after collision has the same speed, different velocities in random direction. Okay, so at any given time, if we consider the ith electron where I is equal to 1, 2, 3, so on, that means we are considering any one of the electron, then its average velocity would be given by 1 upon n sigma Vi is equal to 0. Why 0? Because of the random directions the electron has after every collision, though the speed is c. Fine, where n is the total number of electrons in the conductor and Vi is the velocity of the ith electron, that is first or second or third or so on. Fine. So keeping in mind that Vi average is equal to 0, we now supply or give an electric field of E as shown in the figure to the conductor. When we do this, the electron's path can be seen with a green dotted line before and after the collision. Suppose we have started the electron viewing from the position A, then after successive collisions, the electron has drifted from the position B to B dash in a direction opposite to the direction of the electric field. So, in the absence of electric field, the final position of the electron is B. In the presence of electric field, the final position of the electron is B dash. It means the electron drifts due to the presence of electric field in a direction opposite to the direction of the electric field. Fine. So after applying the electric field, the electron drifts. Why? Because the electric field given to the electron accelerates the electron, and the acceleration of the electron is given by F, that is the force exerted by this electric field, upon m, where m is the mass of the electron. So in the chapter number 1 we have learned that the force is charged into or multiplied to the electric field. Here the charge is that of an electron, which we write it as negative E. Electric field E is given and m is the mass of the electron, where here we have substituted Q is equal to charge on an electron and m is equal to the mass of electron. Fine. Okay, so this is the acceleration given to the electron in a conductor due to the electric field. Fine. Okay. Now let us consider again ith electron whose velocity is Vi just after collision. Same as this Vi, just after collision. So Vi is the velocity of ith electron just after collision. Then capital Vi, which is the velocity of the electron, of the ith electron, in the time t, is given by Vi, capital Vi is equal to the velocity just after collision, which is small vi, plus the velocity of this ith electron at the time interval ti between two successive collisions. Fine, which is given as negative ee acceleration, which we wrote just now, multiplied by the time interval. Fine. Okay. Now let us take an average of all the terms in this equation such that we get the drift velocity of the electron. So the average of Vi is Vd, the drift velocity of the electron. Here Vi average is 0 plus I have averaged only the time for the particular electron. Therefore, I can write EE upon M Ti average, which is tau. Therefore, Vd is equal to negative EE M upon M tau, where tau is the relaxation time between two successive collisions of the electrons. Now let me explain what is this relaxation time. Okay, consider a ion 1 and a ion 2. We have this ith electron colliding the ion 1, then going to the ion 2 and colliding. Between two successive collisions, this electron has spent a time. The average of all the time spent by the electrons between two successive collisions is called relaxation time, which is denoted as tau here. So, we have Vd is equal to negative Ee upon m multiplied by tau. So, Vd is the drift velocity of the electrons, which is an average of the velocity of each electron at the time t. Fine. So, in short, let us go through this explanation where we said the electrons collide with ions and move in random directions after the collision such that their average velocity is 0 because the directions are random. Now let us give an electric field to it such that due to this electric field the electrons accelerate and the acceleration is given by negative Ee upon m. Because of this acceleration, let us find out the velocity of each electron, that is as given in the equation. Then take the average of each term such that we get Vd is equal to negative Ee upon m tau, where tau is the relaxation time, which is the average of the time spent by the electrons between any two successive collisions. So, I hope you have understood this concept of Vd. Remember this formula very strongly. This is a derivation which can be asked in the board and can be asked to apply in the entrances. Okay, so take a pick. I shall just move. Keep watching the video till the end so that we derive related formulas with drift velocity for current and mobility. Now let us derive a relationship between the drift velocity and the current in a conductor. Now as you can see, there is a conductor here. We have given an electric field of E in this direction as shown. As soon as we give the electric field, the electrons will drift. Fine. Let the cylinder have a cross-section area of A, which is perpendicular to the direction of the electric field. Okay, so let us write down what we have. A is the cross-sectional area. Now let us consider a time delta t in which time interval delta t in which we have supplied a electric field of E such that the electrons have drifted a distance of delta x, which is the length of the cylinder or the conductor which we have considered, where Vd is the drift velocity of the electrons due to the presence of the electric field. So, here delta x is equal to Vd, delta t is the distance moved by the electrons. Now, what is the direction of the electrons? Direction of the electrons is opposite to the direction of the electric field as I have shown here. Fine? Okay. Now, let n be the number of electrons per unit volume such that n is equal to number of electrons. Okay, Therefore, we have N is equal to number of electrons per unit volume of the metal multiplied by the volume. What is volume? Volume is distance multiplied by area. Distance is delta x. So N delta x multiplied by area. Substituting delta x is equal to Vd delta T, we have N number of such electrons that are drifting is equal to N Vd delta T multiplied by area. Now, each of these N electrons have a charge of E. So, let us write that Q is equal to negative E N V D delta T A, which is the total charge which is moving against E towards the right. Therefore, in the direction of the electric field, the charge is given as plus E N V D delta T A in direction of E. This is opposite to direction of E. Fine. So now if I is the current in the conductor, then according to definition I delta T is equal to Q. Q is given, say, in equation number 1. Substituting it in equation which we have just now written, we get I delta T is equal to E N V D delta T A. Fine. Now let us cancel delta T on both the sides such that we get I is equal to N E A V D. So we have I as a current in the conductor related to Vd by this equation I is equal to NeAVd. Fine. We gave an electric field to the conductor, so the electrons drifted. Therefore, it drifted a distance of delta x given by Vd delta T. N is the number of electrons per unit volume. Therefore, the number of electrons is NVD delta TA, such that the charge which is moving in the direction of the electric field is given by the equation 1. But by definition, I delta T is equal to Q. Substituting Q from here, we get this equation. Delta T cancels and I is equal to NeAVd. Fine. So this is the derivation which is important again for the board point of view, and the formula is definitely important for the entrances of JEE and NEET. So I just move and you please take a pic of this. Keep watching the video. Now we continue the video with page number 3, where we derive a relation between conductivity and relaxation time. Now in the previous page just now, page number 2, we have learned I is equal to NeAVd. Fine. Okay. Vd modulus, that is the magnitude, is equal to EE tau modulus again upon m. Substituting Vd in the equation number 1, we have I is equal to N E A E E tau upon m. Then we can write I is equal to N E square A E tau upon m. We have learned that current density is current per unit area. So here we have current per unit area as current density. Substituting the same, we have J current density with density as Ne square E tau upon m. Let us name this as equation number 2. Now in the previous video, we had derived an equation between current density and conductivity and electric field given by J is equal to sigma E, where sigma is the conductivity of the material of the conductor. So substituting this in equation 2, we have sigma E is equal to Ne square E tau upon m. E we cancel, we get sigma is equal to Ne square tau upon m. Here n, E and m are constants. Therefore, sigma is proportional to the relaxation time. Remember this proportionality and equation which will be used in our next video. Okay, then rho is resistivity of the material of the conductor. Rho is the reciprocal of conductivity. So let us substitute. Sigma is equal to 1 upon rho in the above equation such that we get rho, that is the resistivity of the material, as m upon Ne square tau, where we know that Ne and m are constants, therefore resistivity is inversely proportional to the relaxation time. This proportionality and equation will also be used in the next video. Fine, I have joined the formula I, Vd, got J, substituted in the equation, J is equal to sigma E, got conductivity and resistivity. This is what is done in this video. Fine, this is also 1 mark derivation question. Okay, so I hope you have understood this concept and this proportionality, which is useful both for the board and the entrances. So I shall just move, take a pic and keep watching the video till the end. In the next page, we will derive a relation for the mobility of the charge carriers. Fine, please take a pic. Now in this page, we shall discuss about mobility of charge carriers. The charge carriers move or they are mobile because of the conductivity of the conductor. Okay, so mobile charge carriers are due to the conductivity available in the material. Now, for metals, these charge carriers are electrons. For ionized gas, these charge carriers are electrons and positively charged ions. For electrolytes, these charge carriers are both positively and negatively charged ions. Mobility is denoted as mu, which is defined as the magnitude of drift velocity per electric field. Therefore, mu is equal to Vd modulus upon E. Fine. The unit of mu is meter square per volt second, but in use it is 10 raised to 4 centimeter square per volt second. That is the unit used. Fine. So this is the formula for calculating the mobility of charge carriers. But we have learned the formula of Vd in the very first page of this video, which is given as E tau upon m. Let us substitute Vd in the formula of mobility such that we get E tau upon m divided by E. E cancels. So we have mobility mu is equal to E tau upon m. Fine. So mobility also depends on the relaxation time tau, because E and m are constants. Fine. Mobility is always positive because we are talking about only the magnitude part. Fine. Okay. So mobility is Vd upon electric field given to the conductor, and when we substitute Vd, we get mu is equal to E tau upon m. So mobility is directly proportional to the relaxation time. Fine. Okay. So I hope you have understood this concept. Please take a pic as I move. Keep watching the video till the end. In the last page, we shall just quickly write down the formulas which we have derived in this video on different pages. Now let us quickly write down the formulas which we have derived in this video. Page number 1, we derived Vd is equal to negative E tau upon m. Fine. Then we also derived in the next page I is equal to NeAVd. We also derived in the next page J is equal to Ne square tau E upon m, where J is the current density, substituting Vd. Okay. Then we derived a formula for sigma, that is the conductivity, which is equal to sigma is Ne square tau upon m. Then derived a formula for resistivity, which is equal to reciprocal of conductivity given by m upon Ne square tau. Then we also derived a formula for mobility, or we defined a formula for mobility. Mu is equal to Vd upon E. such that mu is equal to E tau upon m. That is the relation which we have derived. Keeping n, e and m constant, we can also write sigma proportional to tau, conductivity proportional to relaxation time, resistivity rho proportional or inversely proportional to the relaxation time, and mu directly proportional to the relaxation time. So these proportionalities also are to be used for the various formulas or the various application questions for JEE and NEET very quickly. So this is a quick revision of the formulas that we derive in this video. Fine, take a pic, I shall move.